Thank you. Can you see that?
Yes.
Excellent. Yeah, thanks for having me here. So today I'm going to talk a little bit about global glaciers' response to climate change, and really being an ambassador for the global glacier evolution modeling community, and share a little bit about the most recent work that we've done as a community through the Glacier Model Intercomparison Project. I just want to acknowledge Dr. Fabian Massayon from the University of Bristol and Dr. Regina Hawk from the University of Oslo for also supporting this through some of the results that I'm going to show you. So there's been a lot of studies, really just fantastic studies over the last 6 years and even before that. But a couple of studies that I want to highlight. One is a great study by Ben Marzion in 2018 that really showed this direct link that each kilogram of carbon dioxide that's emitted today leads to the melting of approximately 16 kilograms of glacier ice. So you're going to start to see this theme throughout my talk today, is that there's this direct linkage between how much we are emitting as an international community and the preservation of our glaciers. Currently, this is an estimate from 2000 to 2019 that measured the glacier mass change of every single glacier, all 215,000 glaciers globally, excluding the Greenland and Antarctic ice sheets. Those mountain glaciers are losing approximately 300 gigatons of ice and contributing approximately 1/5 of the observed sea level rise. And this was a study that was published in Nature by Roman Huguenot and others back in 2021. Now, the impacts associated with these are quite diverse. We know that they're very large contributors to sea level rise. As we move up to the higher mountains, we also know that they're very important for water supply, for downstream communities, especially in times of drought. And we know that they also lead to really devastating geohazards, whether that be glacier outburst floods or landslides and rock falls and avalanche events as well, due to the destabilizing effects of the surrounding slopes of these glaciers as well. So we talked a little bit about the glacier mass loss. What does this actually look like? Here's a nice study that was done back in 2019 showing what does Great Alesh Glacier in Europe look like back in roughly 2018. On the left, I'm going to show you some very low emissions. On the right is what happens if we keep our current emissions rates. And you can see what happens by the end of the future, right? For very low emissions, we're still going to have considerable glacier retreat, but we are going to preserve some of that glacier ice really at the higher elevations. Well, if we look at our current emissions, if that continues forward through the end of the century, we're more or less losing the entire glacier, right? So here's 2018, and here's 2100. So the key thing to note is that our actions as an international society really control how much of the glacier ice we're going to preserve moving forward for this century and also beyond. Now, back in 2023, we produced a study that was looking at global glaciers and how they were going to evolve for different shared socioeconomic pathways, so different emission scenarios. And one of the things that we did was we took those shared socioeconomic pathways, we took those emission scenarios, and we aggregated them in terms of global mean temperature change. So this is the temperature change at the end of the century relative to pre-industrial levels, just like we talk about in all of our international policy talks, right? So we can see what does the top row is showing in the top left is showing what's the percent mass remaining over 2015 to 2100 for those different temperature change scenarios. So you see that for a 1.5 degree scenario, we're looking at losing on the order of about 25% of our glaciers or keeping 75% of our glaciers. When we go to that upwards of 4-degree scenario, we see that it increases, right? And that increase can go to roughly losing about 40% of our glaciers, right? Or preserving 60% of our glacier ice. Now on the bottom panel, what you're seeing here is the percent in terms of the number of glaciers. So even in a best case scenario, even if we reduce our greenhouse gas emissions, even if we're able to keep that global mean temperature to a 1.5 degree scenario, we see that we're going to lose approximately 50% of our glaciers by number. And that number increases all the way up to close to 80% for those higher emission scenarios and temperature change scenarios at about 4 degrees. The last time I read we're on the order of about 2.7 degrees, somewhere in that range, right? So we're kind of between that orange line of 3 degrees. Closest line here is to that orange line. Now, the amount of glaciers, the number of glaciers of 50%, right, all the way to 80%. It's really quite staggering. We're going to lose half of the glaciers by number. What I want to acknowledge here is that most of those glaciers are small. So approximately 80% of all the glaciers, all 215,000 glaciers, excluding the Greenland and Antarctic ice sheets, approximately 80% of them are less than 1 square kilometer. So they're very small glaciers. Most of those glaciers are going to be lost even in 1.5 degree temperature change scenarios. While the larger glaciers are still going to be there. But as I showed before in that first slide, right, like the Great Alesh Glacier, those large glaciers, they're going to exist, but they're going to retreat considerably as they try to come into a state of equilibrium with the climate. And this is really true everywhere. So what I'm going to show you here is a plot, and it shows really the sub-regional variations of what these changes look like. Specifically, how much glacier mass is remaining at the end of the century relative to present day, relative to roughly 2015. And so the red colors are showing you areas where we're losing on the order of 80% or more of the ice in that area. The blue colors are showing you where we have less than 20% mass loss, and the yellows are really in between, okay? And the other thing that we flag here is when you see a white circle surrounded that's outlined in black, that's showing where the glaciers in that area are completely lost. So here's what it looks like for a 1.5 degree scenario, 2 degrees, 3 degrees, and 4 degrees. So I'll show that one more time. Here's a 1.5 degree, for example. Maybe we'll look at Central Europe, right? We see some orangish colors, so on the order of 70–80% glacier mass loss in that region. You see that as we go to 2 degrees, 3 degrees, and 4 degrees, we're nearing complete deglaciation of the entire region. As I mentioned before, if we are able to limit our temperature increase, then we're also going to reduce the glacier's contributions to sea level rise. Even in the best case scenario, we're looking at the glaciers contributing approximately 90 millimeters to global mean sea level rise. But for a 4 degree scenario, that can go up to about 150 millimeters. So you see every increase in temperature really matters, or every reduction in temperature really matters. Now, the most recent glacier model intercomparison project was really looking at what happens if the climate were to stabilize. So how much ice would remain if the global mean air temperatures were to stabilize at present day temperatures or at policy relevant levels? So things like a 1.5 degree or a 2 degree scenario like I've been showing you. And this work is currently in review in Science. So this is the type of study that we did. So we ran constant climate scenarios ranging from anywhere from about 0 degrees, so roughly no change above the pre-industrial level, to approximately 7 degrees above. And we run this out to steady state. So we do these model simulations for 2,000 to 5,000 years. And that steady state just is, when does the glacier mass remain constant? When is it in a happy place? It's retreated to a higher elevation. Some glaciers are lost completely, but the glacier mass globally is not changing. And we refer to the difference between that steady state glacier mass, so what happens really at the end here, relative to the initial mass. That's what we refer to as the committed mass change. It's the difference between that steady state and our present day estimates. And so you can see here that even if we went back to pre-industrial levels, that would just be needed in order to maintain where the glaciers are at. It's a lot easier for the glaciers to lose mass, right, than to gain mass and grow glaciers. It's a lot more challenging. A 1.5 degree scenario, we're looking at about 50%. And when you go all the way to higher temperature change scenarios, you can see we're losing a lot more, on the order of 80% being committed mass losses. Here's another way of looking at these plots, right? Committed mass loss at today's warming. We're already looking on the order of losing about 40% of our glaciers. In this middle area here, we're showing that what is the temperature at which 50% of the glacier's mass is lost. So you can see that a 1.5 degree right here is really our last chance to save 50% of the global glacier ice on long terms, right? So this is different than the original projections I showed out to 2100 for the emission scenarios. This is what happens at a 1.5 degree if it stabilizes. And we can look at sub-regional variations for a lot of mid-latitude regions. We see that keeping a 1.5 degree temperature change increase is really the only way to preserve remnants of glacier ice in these regions. Even when we get to 2 degrees, where you see these yellows, we're starting to see that a lot of the glaciers in those areas are almost completely gone. It's also super important for our world's water towers, right, in high mountain Asia, in the southern Andes, right? every increase in temperature matters, or every reduction in temperature really matters and shows what's going to happen to these glaciers in the future. So again, as I mentioned, every reduction in temperature really matters for preserving our glaciers, both by the end of the century, as well as long-term, well beyond it. And be happy to talk about this or take any questions at the end. Thanks a lot for having me.
Thank you so much. That was very depressing in some ways. But it's nice to see the projections for the future if we don't do something serious about reducing emissions. So thanks a lot for that perspective, David.